time for some encoding and a little bit more about modulation. Talked about it a little bit in the physical layer already, but we'll talk a little bit more about what a modem does. So encoding. Why do we need encoding? Well, the reason we need encoding is that people, humans, us, me, you, do not write in ones and zeros. We don't speak ones and zeros. We don't use ones and zeros for basically anything. If we want to communicate, we use our own languages. And we can use English, we can use Arabic, we can use Chinese. There's a lot of different ways that we can communicate. We can use emoji, and those are another way that we can communicate. And the problem is that computers don't speak English or Arabic or Chinese very well. We've gotten closer, and we've gotten to the point where they've started to speak these languages, but they don't speak them the way we speak them. They speak them and understand them in ones and zeros. Well, encoding is the way that we take these languages that we have, that we use, and transform them into a way that the computer can have them, store them, understand them, process them, deal with them, whatever. So, the most basic kind of encoding, the earliest kind of encoding well, it's not the earliest, there were lots, but one of the most common is called ASCII, and I don't remember what it stands for. And it used 7 bits to represent characters. I'll show you the ASCII table in just, well, let's show it right now. These are the ASCII characters. These are the characters that you can represent in 7 bits, because in 7 bits we have between 0, all zeros, and 127, all ones. And the thing is, we need more than just characters. You see the characters start at about, 21 in hexadecimal, or 33 in decimal? From there on, we've got a bunch of characters. These are the things that you recognize. If you look at your keyboard, you'll see most of these. What you may not think about, what you may not realize, is that computers need to be able to speak basically anything. They need to be able to understand everything that's going on, including backspaces. You need to be able to tell the computer to send a backspace, or a delete, a forward delete, or these control characters, or escape, or all these other things. So we don't just have characters to be represented in ASCII. We also have to represent all of these other things, because if you're communicating, if you're storing anything, if you're communicating anything, you need to be able to send all of these commands or characters across a network or within a device. So we've got all of these. That's the characters that you can represent with ASCII. Well, you might see a problem with that. The problem is ASCII works fantastic as long as you only want to speak English. There might be other languages that work in ASCII. I don't know. But English works fantastically with these ASCII characters. These are the kinds of characters that we use all the time. But even if you want to use other characters that use this alphabet, or other languages that use this alphabet, like Spanish, you might need some other things like accent markers to put over these characters. And none of those can be represented here in ASCII. So that's why we have other standards. ISO 8859 took those 7 bits of ASCII and said, why don't we add one more bit to that and get double the number of characters to represent and include a whole bunch of things like those accent marks that I was talking about. Put tildes, put I don't know what they're called. All those little accent marks that you use in other languages, maybe a division sign, an umlaut, that other languages that use the same alphabet as the ASCII alphabet, but add those other characters to that. And that is what those other things do. Which is fine. It's just not quite enough. And the reason it's not enough is that people don't just speak English. And there were other encodings. There are other encodings. So other countries had their own versions of ASCII that had, they didn't call it ASCII, but their own versions of more or less the same thing that represented their alphabet. So there was probably some sort of Arabic version of ASCII that represented Arabic characters. And you were able to encode Arabic information, Arabic characters, Arabic words, Arabic whatever in ASCII or in their own version, in their own encoding. Sorry, I keep reverting back to ASCII. It's not all ASCII. ASCII is just that one. Well, the great thing about the internet and spreading network communication to everybody is that now we want to all be able to use the same version of stuff. And if I send an ASCII document to someone else who doesn't use ASCII, then they're going to open that document and possibly see just a bunch of gobbledygook if their computer isn't able to decode that ASCII. And in other words, to convert the ones and zeros on the computer, on the hard disk, into, or in memory, into the characters that you see on the screen. And so we needed a standard, and the standard that we use now is Unicode. Now I'm going to pull up the Unicode table, if I can, and pull it right over here. Now if you look at the Unicode table, at the beginning of the Unicode table, you've got basically ASCII. All of the same characters at all of the same points that you had in ASCII, including the delete, the backspace, and all those other control characters, along with the upper and lowercase alphabets that we use. And then you see the accent marks that come after that. And then after that, you're going to see a whole bunch of other alphabets. And this table is awesome. And it shows you just how huge Unicode is. Now, Unicode uses up to 4 bytes. So remember, the old ASCII used 7 bits, less than 1 byte. And then we had the ISO standard that used 1 byte. Now, Unicode needs a lot more information to store all of these characters, including a whole bunch of other alphabets. This looks like Batak, which is, I don't know where that is, language for some country. This is some Latin extended characters. If we keep going down, we've got Roman numerals encoded in ASCII, letter-like symbols, math things, arrows, division, all sorts of math symbols. You get the idea. It just keeps going. It's a lot of information that could be stored there. At least 1 million different values that can be stored in Unicode, including something you may recognize, emoji. Now, to send an emoji between an Apple device and an Android device, we need some sort of standard for communication, and Unicode is that standard. So Unicode specifies this description: grinning face with smiling eyes. And then each device or font, essentially, that creates the representation that we see of the emoji can choose what it looks like. So Apple, this is a grinning face with smiling eyes. Looks like a grimace to me, but Apple thinks that's a smile, so we'll give it to them. Android, old Android, you had this gray Android-y thing with grinning face and smiling eyes. And the newer Android has these. You get the idea. And if you scroll down, all of the emoji are code points or symbols specified by Unicode. And they look different on different devices, but that's essentially just the font. The same way that if I display an F in Times New Roman, it looks different than an F in Courier New. It's just a different font to display to change the way it looks. It doesn't change the character that's being stored on the disk or at the computer level. So Unicode is that global, more or less standard that allows us to use the same encoding to transform all the languages onto a disk for a computer, so that using Unicode, I can write my thing in English, I can send it to my buddy in Japan, and he can open that, and it's encoded in a universal format, so everybody can open that and see the same thing, as long as they can display the characters. So encoding doesn't just apply to text. A codec, you might have heard of, or a coder decoder, is a method for transforming things, transforming analog things, whether it's words or audio, images, video, into a representation that the computer can handle. Because computers don't deal well with physical reality, right? We have to teach them how to deal with that, and we do that using these codecs. So MP3, for example, is a codec, and it's a method that tells the computer how to take audio and store it in a whole bunch of ones and zeros. Audio, when I speak it, isn't ones and zeros, but audio, when it's stored on the computer, is. Vorbis is another one. If you've heard of that one, that is the audio specification, a different audio specification to say how to store the waves that I'm transmitting with my voice on a disk in a whole bunch of ones and zeros. Images, you've got JPEG, PNG. These are codecs for storing images. And each of them is different. They have different methods of translating pictures into ones and zeros on a computer. But they do the same thing in the end. Video, we've got the same thing. MPEG-4 has a video specification. H.264 has a video specification. And these are different methods for encoding, translating real-world things into ones and zeros on a computer. Decoding is just the process of translating it back from ones and zeros on a computer to the real-world things like an image or whatever that I want to see. And the modem we talked about is modulating and demodulating. When we talked about the physical layer, we talked about the modem. Modulating and demodulating is just the process of, well, modulating is taking a digital signal on the inside of your network, like on the top on our diagram here, ones and zeros and voltages, and translating that into waves or an analog signal that something outside of our network speaks. So inside of our network, we're using ones and zeros, right? Voltages, the way that Ethernet works, the way that our physical layer works inside our network is through these ones and zeros. It's a digital signal. But outside of our network, for example, over cable, we're using an analog signal. I told you it's frequency in a coaxial cable. You might use amplitude modulation instead. And if you've heard of AM or FM radio, that's exactly what it is. AM stands for amplitude modulation. FM stands for frequency modulation. And that just says, how are we encoding information in these waves? Is it through changing the amplitude, the size up and down of the waves? Or is it changing the frequency of the wave? And you can change it those ways. There's other ways to encode information or modulate information, digital signals into analog signals. But amplitude and frequency are the ones you're probably most familiar with. Demodulating is just the process of converting that back from analog into a digital signal. And that's encoding and modulation.